Good morning. First of all, thank you to the organizers for this invitation and welcome. Good morning to all of you, the audience. I am particularly pleased that I have a chance to talk to this very broad formal methods community, because what I want to do is I actually want to rally the formal methods community to start looking in more detail at what's happening in AI, and okay. Sorry. Let me just. Okay. And particularly machine learning. Is that better? Yes. Yeah. Okay. So let's get started. Okay, if I say AI now, everybody assumes that it's deep learning and machine learning. But of course, AI started off with logic, and formal methods are founded on logic, but we seem to have forgotten because the deep learning giant seems to be beating up logic and formal methods. And I think what we need is actually we need to respond and start dealing with those beasts the same way that we have managed to tackle software verification, which is now, being used in many industrial settings for, critical situations. But right now, everything is about data. Everything is about inference. We tend to estimate, we tend to compute the proportions. We don't know what we are actually classifying, but we should. Why? Because we now have deep learning with everything, and in particular, we have deep learning with safety critical or privacy critical applications. We have face recognitions. We have autonomous driving. We are also looking at deep learning in medical diagnosis. And this is, very serious, very safety critical. And the formal methods community has already contributed in a significant way to actually improve the safety and safety assurance of those devices, but perhaps is not looking at AI as much as it should. Perhaps it's a little bit more difficult, but the stakes are rising even higher. If you look at what Neuralink is doing, okay, so we have deep learning in autonomous driving. It's taking over control from us, but this is looking at brain implants. So you can't really think of anything that's higher stake. Well, the question that I have been asking since I first started looking at deep learning, in particular in 2016, is should we worry about AI decision safety? And I'm showing you some examples here. What you see on the left, it is actually a dashboard camera image, which is then fed into a winning neural network at the time. The winning neural network aimed to classify those camera images into whether they have a traffic light, and if they do, whether this is red or green. And this is quite an old example, and some people tell me, quite rightly, that this is quite an artificial example because, it deals with images. But the software that was implemented by my student uses a very smart game-based search method that can just change one pixel, and that one pixel change catastrophically changes the classification. Okay, so if you think this is artificial, the next example is actually a physical attack. Physical because the image, the 3, has been modified, and this one was demonstrated on a Tesla back in 2016, so I'm sure they've improved. by now. And another example here is the so-called patch attack. So the idea is that, if you have critical situations such as traffic signs, where your decisions completely depend on the correctness of the decision making, what if somebody, actually as a joke or, adversarially decides to put a sticker on this, and that sticker changes the classification catastrophically. And the last example is a real traffic sign in Alaska, because apparently in Alaska they shoot at traffic signs. Okay, I think this indicates the challenge, I think, in the problem, but the point that I'm trying to make is that for high-stakes applications, we actually need provable guarantees. We need provable guarantees on the correct behavior of deep learning components. And this is why I'm particularly pleased to talk to all of you, because formal methods is a very broad community that is concerned with rigor and would actually be able to provide such guarantees. Now, at the same time, the AI and machine learning community is racing ahead and focusing on performance rather than such guarantees. Now, I already know that formal verification is actually very good at providing formal, provable guarantees. And these guarantees can be applied to transition systems, logic-based systems. They can also apply to real-time systems, that picture in the middle, probabilistic systems. And what the rest of the talk will be about is to what extent we can take it to deep learning systems. Now, for this formal verification, we apply rigorous mathematical abstraction techniques. And the idea is that with something like verification, we use tools, software tools, SAT, SMT, constraint solving, perhaps model checking, to actually prove that the system behaves as expected. But what we also want is we want to be able to synthesize systems or policies that are correct by construction and do it in an automatic, algorithmic way. Now, in my career, over the years, I have developed the PRISM model checker, which focuses specifically on probabilistic systems, and this has been used in many application domains and for many use cases. So one use case is for debugging the protocol, but based on quantitative trends, quantitative information, rather than typical corner cases. The other one here is a secret sharing protocol, and what we were able to do there is to confirm algorithmically a conjecture that was made in there. So I'm showing you this because this is a very complex system. It's a concurrent game, so it's a multi-agent system. Now, another example is DNA folding, where we have been building models, probabilistic models, continuous time Markov chains, and those Markov chains were then used to predict, for example, either DNA folding or the behavior of a molecular walker. And the final example is a pacemaker, okay? A pacemaker, it's a real-time system for which we were able to provide optimal controller synthesis. So these are the successes of something like 20 plus years of my career, plus many, many students and collaborators and people in my group and collaborators elsewhere. But now what we want to do is we want to take that technology and apply it to neural networks. Well, why? Because this technology, logic-based technologies and mathematical abstraction techniques allow us to rigorously build and analyze abstractions of neural network components and AI systems. We know that they can provide provable guarantees, where these guarantees could be yes or no answers. Yes, this behaves correctly. It gives me classification, red traffic light, or perhaps the guarantees are in the form of bounds on the perturbations. So I can only guarantee that network up to, say, 2 or 3 pixel manipulations, or perhaps those guarantees have to be probabilistic. Okay, but they are guarantees. When we have those guarantees, we actually have software tools that can compute those guarantees. We can use them within certification, we can use them within safety assurance, and in the long term, we can use them for correct by construction synthesis. Okay, but unfortunately, the beast on the right is a little different from what many computer scientists, say first-year computer science students, know about, because this is a neural network, and the neural network operates in vector spaces, in real valued vector spaces. Much of computer science is actually based on discrete mathematics, and those students are not very familiar with continuous mathematics. There is a little bit of a dichotomy here, and this is why we probably see more of the growth of that kind of AI, either in engineering or perhaps in statistics. So that's understandable. And I think that needs to come back, I think, into the curriculum. So on the one hand, to us, software programmers, this is a very simple system, okay, because it doesn't have any loops. It's just a function. The problem with that function is that it is completely black box because it's been trained for some architecture using optimization, and once it's been trained, you just can't understand it. And in particular, the answers that it gives you, it will provide via something like softmax, it will provide a vector of these score values, and the decision of the network is based on the output for a classification on the output which has the highest score value. But what if the values are very close together? And this is why we see those instabilities, because with floating point, of course, the idealized network works in real vector spaces, but they actually operate on floating point. Okay, and on top of that, they are very high dimensional. Now, I have to say that since 2017, when I've given a keynote at CAV that kind of alerted the verification community to that, there has been much progress, and there have been numerous tools that have been developed. And some of those tools we are actually building on in here. So what this lecture is going to do is it will stay at a fairly high level, because I assume that formal methods community is quite a broad community. I will focus on methodologies for local, I'll explain in a minute, adversarial robustness, which can be used for certification, but really using what we know more familiarly as verification, formal verification technologies. And of course, this is being applied to an ever broader range of applications and model types. And then I will mention some of our recent work, which focuses on directions that are less explored, and I'll explain them. There's pre-image approximation and quantitative verification, I will also explain. And finally, Bayesian neural networks, which actually have principled uncertainty measures. If you are interested, then most of the talk is based on these papers. Okay, So what is adversarial robustness? I showed you an example of the dashboard camera image where you just change one pixel. So the idea is that to us humans, even if you change the one pixel, there is still the red traffic light in there. So it should be classified as the red traffic light. So what we want from local adversarial robustness is for a particular point, for a particular input, in this case, for a particular, say, traffic sign, or for a particular dashboard camera image, if you give it something that has the 30 speed limit, it should be classified as 30. Now, for adversarial robustness, if you also add noise, this would be an infinity noise, very small noise to every pixel, or perhaps more local noise, like through the patch attack, this should still classify, if we humans classify it as a red traffic light or 30, it should still classify as that. So informally, there is no perturbation up to some bound that results in a misclassification. Now, more formally, I assume that I have a trained neural network. Okay, so this is already a trained neural network, one of those spaghetti connected functions, which is, in this case, a classifier. And I have a region which is centered on that input X, and it has a region, this is typically something like an LP ball, so it could be a Euclidean distance or perhaps L infinity distance around it. And I define local robustness at that point X with respect to that region in this SAT-friendly notation that there is no adversarial example, meaning there is no point in that region which classifies as something else. Okay? So with this hint, what you can already do is you can go and you can convert the constraints in a neural network and then send them to an SMT tool, and it will use linear real arithmetic, and it would actually either find or come up with ansat. And this is what the first methods actually did. So what I'm going to focus on here is actually computing these guarantees, which is, there are no adversarial examples for all inputs in that region. The classification is correct, but there is also a lot of work in the area which focuses on defenses. So you have a neural network, and you might want to do something like post-processing, say randomized smoothing, which would ensure that the post-processed network does not have adversarial examples, but with high probability. Okay, this is deterministic guarantees. Okay, but how do you specify the correct behavior of, so here specifically image classifiers, because we use our human intuition. Okay, we use our human intuition for that. And ideally, what should happen is that the region, this ball around that point, should contain images that are similar. Okay? I mean, they all have to have a traffic light. So they should be clustered according to some similarity measures. And the first problem for us, but also for the whole of the adversarial robustness community, where there are leaderboards, there are tool competitions, they are all for L2, L infinity metrics. Okay, these are only proxies, and they would have nothing to do with the actual semantic information that the neural network learns. These proxies would only work for very small distances. So what we need in the long term is we need to be able to capture the semantic information, okay, which is not done at the moment. So what we tend to do is we work with the neural verification problem, which is defined in a very familiar way. I assume that I have a trained network, which is a function, but here I'm just working with a regression, okay? So I'm assuming that on output, I just have the vectors of score functions rather than the classification. And what is verification? Well, you have the component is that neural network, and now you need two predicates. You need an input predicate and an output predicate, and the verification is defined in a very familiar way, which is for all inputs, the output must satisfy the post, the 5 posts. So what I'm going to do for neural networks is to, for now, simplify these predicates into simply polyhedral inputs and outputs. And that's what most tools do, okay? So if you have a look at an input, what happens is, well, if I have an input, such as an image, that's a point in a vector space, and I can then take a polyhedral, even polytope, because it's bounded. So I just take the set of all the points that are within, say, some small L infinity distance from that point. That's for the noise. And for the other one, well, there is, for some, that point plus in the patch attack, okay, all those points that are attacked, okay. These are polyhedral sets. And on output, what I have is, because I'm working with the score vectors, the correct output, in this case, if I want to get the 30 limit, that would mean that the score for the 30 limit is higher than the next score, okay? I've written down what that would mean just at the logic level for m equal 2, but of course that can generalize. Now, typically, if you want to work with something like constraint solving or SMT, then this is intractable. So what we tend to do is we tend to just lower and upper bound it, approximate, because that still gives us some guarantees. And usually what the neural network verification does is it proceeds forward. We have a function. I've now got a specification, which is an input polyhedral set and an output polyhedral set. I start with this input just in a way that abstract interpretation works. And then I just bound the worst case for each layer. I propagate it. And what I get is the worst case on the outer layer through that propagation. So what I get is not the precise output specification, but an over-approximation. And in fact, what is being observed is that this may result in very loose bounds. So it is an issue. So most techniques that have been developed, they actually do not focus on computing the exact bounds. They focus on computing some lower and upper bounds on the minimum and the maximum of the reachable set. Okay, the reachable set meaning the set that the neural network maps the inputs to. And the range of techniques includes search-based techniques, constraint solving, say SAT, SMT, mixed integer programming, etc., and abstract interpretation. There is also global optimization. But the tool that performs best is convex relaxation. So what convex relaxation does is it deals with nonlinearities, that is the nonlinear activations, such as the ReLU activation that is shown there in black, and relaxes them, approximates them in terms of either intervals, that would be, if you know abstract interpretation, that would be the box domain, okay? Or linear bounds, which is what I'm showing you there. Now, there are several approaches to convex relaxation. They all, for ReLU, they all tend to agree on how the upper bound is computed, but they differ in how the lower bound is computed because there is no unique way to lower bound a ReLU. Okay, so tools such as Crown slightly differ from what Deep Poly is doing. So they are the best performers, but still scaling and complex architectures are needed. And what we need is also complementary techniques. So one recent complementary technique that we have developed is actually automatically configuring convex relaxation for sigmoid nonlinearities, so that you can improve the precision of the lower bound. What is involved in that? Parameter search to actually find the best alignment of the linear bounds around the sigmoid, okay? But of course, even that is not sufficient. So sometimes we may need to resort to testing. And for testing, I mention here some recent work which prioritizes the test case selection, uses heuristics based on estimating uncertainty in the sense of how much noise there is in particular features, and then prunes features that are noisy, and after it's pruned those features, it produces another probability vector. And that then is shown to improve the performance of the network. Okay, now so far, all the methods that I've shown you worked forwards. But if you are familiar with model checking, symbolic model checking in particular, say the first successes of symbolic model checking actually started off with a backward algorithm. So if you want to prove that your software is safe, rather than going forward, which would be undecidable with software, not here, you start with all the unsafe sets, and then you step backward, okay, through the transitions. And then, you check whether the initial states or the states you are interested in are actually contained, in the safe pre-image, okay? For some reason, pre-image and this backward analysis has not been applied in the context of neural network until last year, okay? So rather than starting with the input set and going forward, we are starting here, okay, with the polyhedron set on the output, and we'll be computing a kind of actually a disjoint union of polytopes in the work that we've done on the input, which approximates the pre-image, because the computation of the full pre-image is intractable. So we need to be able to deal with this. This would give us, of course, the property that anything in the under-approximation is guaranteed to be correct, is guaranteed to give you the correct answer with respect to the specifications. Okay, right, so what do we do with this? So we actually utilize convex approximation, linear bounding, and this is the tool known as CROWN. Actually, more specifically, its extension known as alpha-beta CROWN, which can also work backwards. So we start with a polyhedral property, and then we compute backwards symbolic lower and upper bounds for the individual activations. Now, for each individual activation, if you go from the output set for each activation, you compute a single polytope. Okay? So what we do is, we start with approximating via a large polytope, and then using this symbolic information here, refining this one big single polytope according to those symbolic lower and upper bounds. And there are in particular two ways to split this. One is to split the polytope on input, and another one, I would say, is actually to split the ReLU, and you will see in a minute what I mean. Now, what this approach involves is actually the underlying computation grows exponentially in terms of the number of constraints. So what I have is I start with some initial approximation, okay, some initial polytope, and I said I'm going to keep splitting until I reach some point, or I've run out of resources. This is any time. And then once I've split enough and decided to stop, I can then put together the individual polytopes into a refined approximation. Now, this approximation can be either an under-approximation of the preimage or over-approximation of the preimage. So what is the key to the success of this tool? The first one is that the splitting splits the regions in such a way that they can be handled in parallel. So they can be run on GPUs. But the other one is that I can do ReLU aligned cutting plane, and ReLU aligned cutting plane just aligns with the linear bound in there. So what the conventional linear relaxation does is produce these bounds, which are very approximate. But if I can split according to here, for an unstable neuron, I have two exact approximations, okay? For stable neurons, I have two exact approximations. Now, in addition, what I also need to do is I need to optimize these slope parameters, because these slope parameters allow me to improve the volume of the under-approximation of the pre-image. Intuitively, I want that volume to be as large as possible, so as close as possible to the full volume, to the full pre-image. So what we tend to do is we tend to use various heuristics and optimizations, the selection of the splitting regions, and we use volume estimation to guide the search. But once you've computed the disjoint union of polytopes, you need to compute the exact volume in order to retain the soundness of the method, logically the soundness of the method. So how does it work? So for example, this is the first method that scales to L-infinity attack and also to the patch attack. I'm showing you pictures from GTSRB, which is a traffic sign data set, because that work is in progress, but the paper talks about NIST. And as you can see, what we get is that sometimes you have an approximation which is a very small number of polytopes that under-approximates the region of the pre-image that you are interested in, okay? But the growth is there. In the worst case, grows exponentially. But the most interesting thing, which you do not have with conventional robustness verifiers, is we also have the coverage approximation. So that 100% is up to the sampling volume, but even 75% might be useful information for many applications. And this is why we can also use this technique for what we call quantitative neural network verification. So I've given you the logical formulation of neural network verification, and then the answer would be yes or no, okay? So what if the answer is no? I can still get something less than 100%, but perhaps it's 90%. Perhaps that's good enough, I think, for many applications. For safety critical, you would probably want 4 nines. But if it's not safety critical, perhaps you can get away with 75%. Okay, so that's the idea. And we've also done a comparison with Alpha Beta Crown, which was the winner last year of the competition. And they are, of course, they are very different. What we are doing is we are not competing. We are providing complementary analysis, which provides you these coverage estimates. Okay, right, so this was the first part, pre-image, which I think is worth looking at in more detail, and quantitative verification. Now, if you think about quantitative verification, well, this is quantitative verification which is applied to a deterministic network. And I started off with deterministic guarantees, then provided these quantitative guarantees, but can we really expect neural networks to provide good, reasonable, deterministic information? Okay? I mean, what about uncertainty? We know that neural networks are trained from data, so there has to be a lot of uncertainty. There could be noise, but there could also be uncertainty because there were some key data points missed out. Okay, this is a more critical uncertainty. So ideally, what you would like to do is to work with neural networks which have uncertainty as a first-class citizen. And such a notion already exists. And mathematically speaking, it is relatively easy to define. You just take a neural network and put a prior. Okay, so rather than having individual values for weights, you have random variables. You have random variables over weights. And then if you know about Bayesian inference, once you've put a prior, you can use this information to compute the posterior. Of course, assuming tractability, But mathematically speaking, this is, very elegant, very neat. And the information that it gives you is a probability distribution in a way that the softmax values are not, because the softmax values are not probabilities. They are just relative weights of the outputs that you want to get. They are not probabilities. Here, if you do this trick, so work with random variables, have a proper Bayesian prior, compute the posterior, you get a probability distribution on the output. Okay? I'll show you in a minute what difference does it make. But what I'm going to do is I'm now going to define, say, robustness or safety, but just with some probability. And that probability is conditioned on the training data. So the generalization that I'm working with is, before I was saying there does not exist a point y where the classification differs, because I wanted to send it to SAT SMT. But now I'm saying, well, that the probability that there is a y which differs from that point x, that's the output differs on, is, say, small. If you want it to be safe, you would want that probability to be small. And anyone who's worked with, say, safety engineering would be familiar, with this kind of formulation. What we want to do through this work is actually, we want to provide certified bounds on decision probability of individual Bayesian neural networks. But another aspect that, if I have time, I'll mention is certifiable adversarial robustness training. If I don't, this is just a generalization of adversarial training, but to Bayesian neural networks. Okay, so I've already explained, what a Bayesian neural network is. This is just formalizing it. So in order to infer the weight parameters, which are now random variables, that's why they need Bayesian inference, I start with a prior. Now, I said that prior, this is a Bayesian neural network. That prior is over weights, but the actual prior that you need here is a prior on functions, okay? Because we are talking about a component which is a function, and the prior, should pre-select functions from that set. So there is already a little bit of ambiguity here. What I also need is the likelihood. Okay, this is the standard likelihood in Bayesian inference, and I can approximate the posterior distribution by Bayes formula in a standard way. Mathematically, this formulation is completely standard. I just simply integrate the likelihood with respect to the posterior. Of course, this integration for large neural networks is not going to be tractable. And it is a challenge that I'm presenting to you. Perhaps there are people with the right backgrounds to actually start working on that. Okay, so once we have the posterior, which we can approximate, I can't say compute, we can approximate, and sometimes we cannot even approximate with guaranteed bounds because of the complexity of the system and Bayesian reasoning. We can then use the posterior predictive distribution for an unseen point and then compute the prediction. Okay, and that prediction is then going to be a probability distribution. Okay, now that probability distribution depends on the loss function. So if I'm working with a regression neural network, which has as an output vectors of, logits, then I can simply take expectation, okay? Just take expectation of that value. But for classification, this is a bit more involved because classifiers are trained with 0-1 loss, so you actually have to maximize the predictive distribution actually with respect to the softmax, okay? Now, why do we want to work with Bayesian uncertainty? Well, in deterministic neural networks, if you take a classifier, say, that predicts red light traffic lights, what if the values, the softmax values are very close? That means that depending on what system your network runs, you'll have different answers, okay? Sometimes it would give you red traffic light, sometimes it would give you green traffic light. So softmax in deterministic cannot accurately capture the confidence in the prediction because it's just, if you want to compute some confidence, it would give you that mean. But for safety critical analysis, what we need to be concerned with is actually worst cases. And if my distribution is like this mean will be completely misleading, okay? So imagine you are, sitting in an autonomous car which is making decisions based on that mean. What the controller is telling you here, turn left or turn right, okay? But the decision will, oh, I want to go straight because that's what the mean tells me. So that is wrong, okay? So for this, what we also introduce is we introduce analogs of robustness for these Bayesian neural networks. And the first one is very similar to the quantitative verification that I've mentioned, which is computed using completely different means, and of course the underlying beast is different. But the idea is that I, again, have two sets, and just imagine these sets T and S are polyhedral. And I want to compute the probabilistic robustness by computing the proportion of neural networks sampled from that Bayesian neural network. Okay, so remember the weights are random variables. If you sample, it will fix the weights. So for each of those neural networks, you can compute the value, and then you just sum up, okay, estimate the probability, the proportion of those that actually meet the specification. That is, they map inputs in S to outputs in T. Okay? Now, this is actually a property of the network, but not of an individual decision. Okay? It's not going to help us with the problem that I showed you before, the mean problem, because it would still give you the mean. So what we need to do is we need to have decision robustness, and decision robustness is a stronger property which actually computes the expectation, okay, of the specification. And the specification is for all points in T, they are going to end up in S. But because I'm working with probability distributions, I just compute the expectation. Well, in fact, I actually compute the minimum and maximum value over the target set T. Okay. And here, just to show you, the mean is the dashed line, but with decision robustness, I ensure that that set T is always on one side of that line, which you cannot ensure with the other formulation. Okay, well, computation of robustness properties is very involved because the underlying computation of the integral is intractable, and for that we need smarter and more smarter techniques to develop. So we use, for example, statistical estimation, which is known as statistical model checking. So you sample the neural networks from the Bayesian neural network, and then you use some hypothesis testing in order to estimate the probability of satisfying the specification. But there is also another approach, and that involves computing the lower and upper bounds. And in this case, interestingly, it uses the same kind of bound propagation that I've mentioned before, but it only goes forwards. So it can work with interval bound propagation and also linear bound propagation. And there is some work done recently by Luca Laurenti, which applies dynamic programming. Now, these will produce sound, provable guarantees, okay, and they would capture the worst cases. So you don't have to worry about, say, being sent straight by the autonomous car, because this kind of decision will consider the worst case possible output. Okay, and what have we done with this? Well, we have applied it to a number of problems, and we'll start with the first one. So everybody knows about MNIST, I think. MNIST, the images, handwritten images. This is something called MedMNIST. This is a data set that was created for medical images, and you are looking at a pneumonia subset of that. And of course, they come, with ground truth information, so they are very useful for benchmarking. What they also have is different image resolutions, so they are very good for testing the limitations of the method. As you can see, you can get decision safety, but only for very small regions around the point, okay? And that just drops to 0 because the method, well, I mean, we are working with floating points, so approximation is just killing the results at that point. So we need to be cleverer there, but we have not tried the backward approach here. And another, I'll finish with this. This is a GTSRB, which is a German traffic sign recognition benchmark, and it's trained on a 3-class subset of that image. And with this, we tested it to show whether it can compute non-trivial robustness guarantees. So for decision safety, it computes an upper and a lower bound. And what you want, ideally, is you want the lower bound to be sufficiently high, okay? Perhaps not 100%, but sufficiently high. But you want the upper bound not to be too low, because that means uncertainty. And that's why what you see there is some nonsense traffic signs, because it's testing whether the neural network recognizes uncertainty in the form of out-of-distribution information, which it does, okay, to some extent. So I will skip over the adversarial training, and I didn't say it, but it was on the slides that this was focused on a single-step prediction. There is also an iterated multi-step prediction, which has been applied to a slightly different setting with a Bayesian neural network plays the part of the environment, and the controller is synthesized against obstacles. Okay, and say one final wishful thinking that I will mention is efficient, robust learning. So we know, thanks to people like Leslie Valiant, there are computational learning theories which actually tell us to what extent we can efficiently learn to recognize some systems. But not, until recently, no one was looking at the question, can we efficiently, robustly learn? Okay, robustness. So can we learn in a way that ensures robustness in the same way that I've introduced before, which is it's not susceptible to small perturbations up to some perturbation bound. And we've made progress in there, but this stops at half spaces, okay? Half spaces. So it's nowhere near neural networks yet. Right, so that's kind of, the end of my talk. I just wanted to summarize that, say, there is, as you can see, I think from the media, from the students in the community, there is a lot of excitement about AI and AI deployment. And so, AI is in the news. And I think I just want to kind of appeal to this community that, what we want is, we want AI to be in the news for the right reasons, okay? So we want AI to be in the news because it has actually helped in diagnosis. I think what we get is, tends to be things like that. Even Google search feature tells people to eat glue and rocks, okay? So I think this is where I think the formal methods community, I think, has a clear role to play because of the focus on rigor, the focus on logic, but it probably needs, people or connections to people who work with vector spaces, continuous spaces and probabilities, continuous probability spaces. So just to conclude, well, I've shown you a range of verification techniques. Okay, everybody would agree that we need robustness guarantees for high-stakes decision-making, but likely, it is very likely that this will not work without human involvement. If you look at autonomous driving, for example, they are stepping back from level 5. I think in the medical community, doctors are not happy about systems not being explainable. So I think there is a lot of work that has to be done there to provide a workable involvement with human decision makers. But, okay, so in machine learning, they just keep improving and building larger and larger systems because they're focused on performance. And we are stuck with CNNs. And just a few layers of CNNs. Okay, I mean, we've made some progress with scene text recognition, which is something that is used industrially. But that's really our limit for now. Nowhere near, what language tools can do at the moment. Nowhere near the complexity. So major challenges remain, and challenges such as, semantic methods, which just have not really started, and probably will not start until we get real, deployment and engagement, I think, from the user community, rather than leaderboards. Yeah, okay, so that's it. I just wanted to show the acknowledgements. Thank you for your attention.
Do we have questions?
Hi, thank you for your nice talk. So, as you mentioned at the beginning, most of the verification tools that are out there are assuming exact real number arithmetic. And, but actually, like neural network are run with floating point or even worse, fixed point.
Yep.
So one thing that maybe I would like to ask you about is that now a lot of industry make quantization of neural network, and they are like assuming that the behavior is the same as the initial one. So do you think that these approaches you presented can be also used to verify quantized neural network, or like can be extended to that?
Yes, so there is work on verification for quantized neural networks. You can look up Tom Hensinger's group. They are also susceptible to instabilities. So I think what you are saying is correct, that industry needs quantization, because industry now needs to be able to put these deep learning models on mobile phones and small systems, okay? So the industry are forced into that, and yes, I won't mention a company, but I did hear about the case where they quantized and they assumed the behavior is the same, but there is no reason to assume. I think, you know, as a minimum, you would need to do some testing. Yeah.
Thank you.
Hi, thanks for the talk. I had a question about the connection between explainability or some formalized sense of explainability and verification. One of the benefits of verifying something like software is that if you get an invariant that works out of it, that is also a view into what the program is actually doing. But we don't. Do we have anything similar in this in the space of neural networks? Or is it? Do you think that it will be possible to or useful to do that?
Right. So explainability is an umbrella term, and it means different things to different people. I think what, for example, medics would like to have is a simple decision tree, so they see every decision point and why that decision is made. And I think it is certainly true that there has been a rush because of excitement towards deep learning. And for many of these automated decisions, we don't need deep learning. In fact, deep learning overcomplicates things. I think in many cases, and people are beginning to show that you know, it's enough to work with random forests, you know, decision trees, and that gives you better explainability, also better performance. Just imagine training these neural networks. So I think when these systems get really deployed and taken up by clients, you know, by medics, which at the moment is difficult. It's very difficult to push them. It's easy to say, get a paper and get the results on the leaderboard and the paper in NeurIPS, but it's a lot harder to convince medics that they should be working with that. But talking about explainability, there is also a strand of work, and I didn't mention it here, where you want to use, and again, you would use conventional verification techniques, say SAT-SMT, and that is to compute an explanation of the decision. And that may be a part of the input, and I think that may be useful. I think it's additional information. I mean, I think, you know, such a medical domain, also the autonomous driving domains that we are sort of, you know, used to, and we know that sometimes it will be useful to have additional information. You will never believe, just the value that the system gets you, even if it is, proved correct, the system is proved correct. You'd never believe that. You'll want to have additional information because you know that there could have been various other things that have happened, like, the system, the compiler was different, the system, underlying system is different, the bit were, are different. So we need a whole of tools that would support explainability, particularly in cases like medical image analysis. And for that, we need a two-way interaction.
Thank you for the nice talk. With respect to the semantic methods, did you consider to use robustness verification in combination with testing or statistical model checking for proving input-output specification?
No, so it's only this work on test case prioritization. But yeah, there may be something happening. I think, what VAEs, the encoder-decoder systems, I think if we have some theories that kind of give us, principled information about the features that VAEs produce, both encode and decode, then this will reduce the verification problem to something that will be easily tractable. Because I think for many of these problems, we are over-focused, and the verification community is really over-focused on looking at, ImageNet, okay, pictures, which are also in RGB, so they have huge dimensionality. But in fact, all that matters, maybe, okay, sky, maybe the cat, or maybe cat's eyes. So the dimensionality will be hugely reduced, but we would need to have a VAE with some guarantees that the semantic features it extracts are correct. Of course, as you can imagine, that depends on the training data that you give it, and also ground truth information.
Thank you very much for your nice talk. I was wondering, actually, in practice, these components, which are learning-enabled, they will be integrated with other kind of software components, right, in practice. So I was wondering whether we are also studying the interaction of these kind of component with other software, not only the external environment. And in this case, do you expect the same techniques to be applicable here, or we should look into something else in this scope?
Okay, so I think I have already practiced answers to this type of question. I've even written in a proposal, in my second ERC grant proposal, that we need to look at interface theories, okay? And I have not managed to make progress with that. So I think people are welcome to consider interface theories that actually give us, okay, I said this talk was about guarantees. They should be assumed guarantees, okay? Assumed guarantees, and they should be for systems which would have deep learning components, would have, conventional components, and you need interfaces so that you can plug them in together. So here, notice that this will not apply in general. This will apply to situations where you can localize the neural networks to separate components. I think what people also want to do, and that's much more challenging, is to combine the neural and symbolic, and that would give you a much more complicated spaghetti than the conventional neural network, okay? So it would not deal with that. But I think for applications, interface theories with assumed guarantees are critical. I don't know, why aren't people working on these sets?
Okay, so let's.
I'm just taking up a minute of your time before the it's not working. I don't think it is. Just a minute of your time before the coffee break. Thanks a lot for the talk. We wanted to leave you with a small memento from the talk. Actually, there's a bit of story, so let me just take a minute of this. You know, Politecnico is an engineering school, but it's also an architectural school and design school. One of our an alumnus of the architectural school actually became famous designer. So he designed this. It's actually a corkscrew. His name is Alessandro Mendini, actually, and this is a fairly famous piece of design called Anna G, actually. So we want to give it to you as a memento for the talk and for the conference. Thanks a lot. For those of you who are not here last couple of days, coffee break.